friends, good morning. This is Jaswinder Kaur and I'm here to teach complex analysis. So far we have discussed stereographic projection, analytic functions, power series, then is Lorentz theorem, singularities, Cauchy's integral, poles, essential singularities and other kinds of singularities. Fine. Today I'm going to present a new topic, contour integration, which includes the concepts of the poles and singularities and Cauchy residue theorems. This topic is again very important and scoring in UGC NET exams. And one more thing, I'm going to say that whatever remarks or notes I mention or display on the screen, you all have to note or write down in your separate notebook, right? Because all those remarks are very important and useful in solving quick objective questions in the entrance exams, right? Okay, let's start with the topic contour integration. All right, again, I'm going to start this topic with the remarks. So take out your notebooks and write them. First one is, if fz has a simple pole at z0, simple pole means the pole of order 1, then residue of fz at z0 is equal to limit z tends to z0, z minus z0 into f of z. This is the formula for finding the residue of fz at z0 if function has a simple pole. What if the function has pole of order more than 1? So second remark is, if fz has a pole of order k at z0, k refers to 2, 3, 4, 5, 6, any number, then residue of fz at z0 is equal to 1 over k minus 1 factorial, limit z tends to z0, and we have to derivate z minus z0 the power k f of z with respect to z k minus 1 times. Right, whatever times we have to derivate, that is k minus 1, that k minus 1 you have to write in the factorial in the denominator, right? So just keep in mind this. And power here is k because we are talking of the pole of order k. Third is, if the function is phi z over gz has a simple pole at z0 where this phi z is your holomorphic function. Holomorphic means analytic function. Then residue of fz at z0 is equal to phi of z0 over g dash z0. That means derivative of gz at z0. For example, suppose I am having a function z square plus 1 over z minus 1 into z minus 2. This is my phi z and this is my gz, right? So I need to find the residue of this function at 2. Okay, so can I write this function as, first I need to solve this denominator, which is z square minus 3z plus 2. And now to calculate the residue of fz, I have to write phi of z0. That means I have to write this numerator at z0, and here z0 is 2. So this is 2 square plus 1 over, and we have to derivate this once, which is 2z minus 3 at again z0, which is 2. So this is equal to 2 square, which is 4 plus 1, it is 5, over, put 2 over here, this is 4 minus 3, which is equal to 1. So the residue of fz at 2 is 5. Fine. Next, again notes. We know that formula for sine theta is equal to e raised to the power iota theta minus e raised to the power minus iota theta over 2 iota, which can also written as, this is equal to 1 over 2 iota e the power iota theta minus, taking this to the denominator, which is 1 over e the power iota theta. right? If my z is in the polar form, so I can have another formula, that is 1 over 2 iota z minus 1 over z. Keep this in your mind because I'm going to use this formula almost in all the examples. Then is the cos theta, which is e the power iota theta plus e the power minus iota theta over 2, which is equal to 1 by 2 e the power iota theta, and this e the power minus iota theta is changed to 1 over e the power iota theta. Again, I am putting this e the power iota theta as z. So this is z plus 1 over z. Please keep these two formulas in your mind. Then cos square theta, we know it is 1 plus cos 2 theta over 2. And sine square theta, again in terms of cos, is 1 minus cos 2 theta over 2. And then fourth one is e the power 2 pi iota is equal to 1. E the power pi iota is equal to minus 1. E the power pi iota by 2 is equal to iota. And e the power 3 pi iota by 2 is equal to minus iota. Just keep in mind this little things, because if you use the Euler's formula for this, that is suppose e the power pi iota, use Euler's formula, which is cos of pi plus iota sine of pi, you will get your answer to be minus 1, right? So just keep these things in mind. Then fourth one is, if you are having the even powers, that is e raised to the power 2k pi iota, the answer is 1 for all integers. This set is denoted the set of integers. And if here you are having the odd power, that is 2k plus 1 pi iota, then this is equal to minus 1. Okay. Sixth one is mod of e the power x plus iota y. This is equal to e the power x. Why? Because if you take the mod e the power iota y, then this is equal to, using the Euler's formula, it is cos y plus iota sine y, the mod of this, which is equal to cos square y plus sine square y under the root, which is equal to 1. So we are left with e the power x. Last remark, Cauchy residue theorem. Integration over c f of z dz is equal to, where c is your circle, 2 pi iota times sum of the residues of fz at the poles inside C. Suppose you are having your circle C mod z equal to 1, and if you are having the pole inside, suppose first pole is your alpha, second pole is your beta, third pole is gamma, suppose outside the circle, then applying the Cauchy residue theorem, you will have to sum up the residues for alpha and beta. Right? The poles which are inside the circle, you have to take the residue of fz at these two poles and take their sum, right? We don't have to find out the residue for this gamma because it is outside the circle. So we find the sum of the residues of fz at alpha and beta. And if there is only a single pole inside the circle, then you have to write only the residue of this fz at alpha and multiply this residue with 2 pi iota. Okay. Let's start with the first example. Show that integration 0 to 2 pi 1 over a plus b cos theta d theta is equal to 2 pi over square root of a square minus b square. The first step is to put z equal to e the power iota theta. But keep in mind and first ensure that the limits should be from 0 to 2 pi, because it is a complete circle from 0 to 2 pi, right? And z equal to e the power iota theta is your polar form. So first ensure these limits that it should be from 0 to 2 pi, and then put your z equal to e the power iota theta, right? So what is dz then? This is equal to e the power iota theta iota d theta. And furthermore, can I write it as iota e the power iota theta is z d theta. Fine. And then this d theta is dz over, taking this iota z to the denominator of dz, iota z. Okay. Thus, this integration will become 1 over, this is a plus b cos theta, 1 over a plus b. Instead of cos theta, I am using the formula which I told you to keep in mind. The formula for the cos theta, that is z plus 1 over z divided by 2. Do you remember? Okay. Check your remarks, okay? Then instead of d theta, it is dz over iota z. Now here C is your circle, unit circle, mod z equal to 1. If you simplify this, you will get 2 over iota integral sign over C 1 over bz square plus 2az plus b dz, right? And I'm going to put this 2 over iota 1 over bz square plus 2az plus b as f of z, because this whole thing is in z. So I'm putting all this to be equal to, taking this as f of z dz, right? So the next step is to find the poles of this function fz, where your fz is, can I write here? Okay, where your fz is 2 over iota 1 over bz square plus 2az plus b. Is it fine? Okay. Now we have to find the poles of this function. How to find poles? Yes. Very good. We have to take the denominator equal to 0 and get the values of z. So in order to find the pole, you have to take the denominator to be equal to 0. What is the denominator here? Put bz square plus 2az plus b is equal to 0. This is your quadratic equation, and from here I get 2 roots of z, which is equal to minus 2a plus minus square root of 4a square minus 4b square over 2b, which is equal to minus a plus minus square root of a square minus b square. 4 is taken to be outside and then cancelling with 2, I am getting this. So I am having 2 roots for this equation. One root is taken to be as alpha, which is minus a plus square root of a square minus b square over b. And the second I am taken beta, which is minus a minus square root of a square minus b square over b. Fine. And alpha and beta are nothing but poles of fz, because we are finding the poles, right? Now to check which pole falls inside the circle, we have to check this, right? Since it is given that a is strictly greater than b and b is strictly greater than 0, so if you check your mod of beta, this mod of beta comes out to be strictly greater than 1. See, what is mod of beta? Mod of beta is equal to, if you take the mod over here, you get a plus square root of a square minus b square over b. Now because a is greater than b, so this a square minus b square is positive. Okay. And also if you see this a over b separately, because a is greater than b, that means your a by b is greater than 1, of course, which implies this, because this first fraction a over b is greater than 1, that means the whole mod of beta is greater than 1. It should be greater than 1, right? Secondly, if you check the mod of product of these two roots, this comes out to be 1. Okay? And because since mod of alpha beta is equal to 1 and mod of beta is strictly greater than 1, your mod of alpha comes out to be strictly less than 1. See, mod of beta is greater than 1. 1 over mod beta is less than 1. Because the product is equal to 1, can I write mod alpha to be as 1 over mod beta? Yes. Because this is strictly less than 1, so what I got? Mod alpha is strictly less than 1. So I'm having two things. Mod alpha strictly less than 1 and mod beta strictly greater than 1. So which of the root fall or which of the pole fall inside the circle? Yes, alpha. Very good. Because suppose this is your circle, z, mod z is equal to 1. Mod z less than 1 means inside the circle and greater than 1 means outside the circle. Because mod alpha is strictly less than 1, so alpha lies inside the circle and mod beta is greater than 1, so beta lies outside the circle, right? So we have to calculate the residue of fz at alpha only for one pole, right? Now, residue of fz at alpha is equal to, what is the formula? Limit z tends to alpha, because we have to find at this point alpha, z minus alpha into f of z, right? So I'm writing here, limit z tends to alpha, z minus alpha, what is my function? It is 2 over iota bz square plus 2az plus b, limit z tends to alpha, z minus alpha, it is equal to, taking b outside as a leading coefficient, so this is iota beta, and this quadratic polynomial is changed into z minus alpha, z minus beta, because alpha and beta are the roots of this polynomial, quadratic polynomial. And z minus alpha is cancelled out with z minus alpha. Okay, we are left with z minus beta. So this is equal to 2 over b iota limit z tends to alpha 1 over z minus beta, which is equal to 2 over b iota. Now putting this alpha in place of z, so this is 1 over alpha minus beta. Now, what is the difference between the roots? If you solve, you know that your alpha is this and your beta is this. Check out their difference. What is the difference? It comes out to be 2 times square root of a square minus b square over b. So it is 2 over 2 times square root of a square minus b square over b. I am taking this b to the numerator and b cancel, 2 cancel, so I am lefting up with I am already taking this 2 in the denominator, so this is 1 over iota square root of a square minus b square. Right? So hence by Cauchy residue theorem, 0 to 2 pi 1 over a plus b cos theta d theta is equal to, which I take this as the form of z, and that is f of z dz, right? This is equal to 2 pi iota times the residue at alpha, and the residue at alpha is calculated as 1 over iota square root of a square minus b square. Is it? Okay. Iota cancel, and I got 2 pi over a square minus b square. Fine. Here ends up the solution. Very easy and very important one. Just go through the steps. You will get very easier to solve this, right? Okay, I'm going to give you some of the exercises. 2 questions I'm giving you. based on the solution is same. Just for your practice, I'm giving you 2 exercises. You have to show that, first exercise, show that integration from 0 to 2 pi d theta over 1 plus a cos theta is equal to 2 pi over square root of 1 minus a square, where your a square is strictly less than 1. Don't worry, you just need to ensure first the limits should be from 0 to 2 pi. Alright, it is there. Okay, same solution is there. You just have to replace your a with 1 and your b with a. Right? Same solution. Then the second exercise, evaluate integration from 0 to pi 1 over a plus b cos theta. Okay, this time I'm writing a plus b sin theta. This should be equal to 2 pi. You have to prove this. That's this is equal to 2 pi over square root of a square minus b square. Everything is same. You just have to write the formula for sin theta, which is 1 over, you have to use this 1 over 2 iota z minus 1 over z. For cos theta, I have used 1 by 2 z plus 1 by z. Now here only cos theta is changed into sin theta, right? So you have to use the formula for the sin theta in this exercise, right? Very, very easy. I know you can all do this. If suppose any doubt, any queries, you just ask me or email me, or I will solve these questions in the next video, right? Okay. Alright guys, thank you. Have a very nice and blessed day. We meet in the next video. Goodbye.